And the problem was we have a cantilevered beam with a length of 2 meters. And we're looking at a line that's halfway along the length, so this is 1 meter. The mass is 100 kilograms. The cross section is rectangular. With a base of 0.1 and a height of 0.5. And when we're doing these rectangular shear force, stress due to shear force calculations, we always want that rectangular shape to be taller than it is wide. And we're looking at a line half of the way from the neutral axis to the top. And we finished the bending moment calculation. We got that I for the cross section is equal to 0.1 times 0.5 to the third over 12, and that's about equal to 0.001041 meters to the fourth. And so the XX stress is equal to positive 5.9 times 10 to the fourth pascals. Okay, so the stress due to bending we're looking at a stress element like this, and we have a positive value. So what direction is the stress on the positive x face? Is it to the left or the right? Yep. So positive, remember, so this is x, this is y. We're talking about the stress coming out of the positive x face, and since it's positive, it's going in the positive x direction. So we have 5.9 times 10 to the fourth pascals. And the other one's coming out the other way, same magnitude. Okay, so now we're going to the shear. So now we're looking for the XY stress due to the shear force. And we know that, so when we did the internal loads calculation, we got that the shear force is equal to negative 490.5 newtons. The absolute value of this stress is equal to the shear force times Q divided by IB. V is equal to negative 490.5. We don't care about, we're just taking absolute values of everything. You could write it like this. I is the same as it was for bending, and so that's equal to 0.001041. B is the thickness of that rectangle, so that's 0.1. So now we have to calculate Q. So what we're looking for here is we're looking for the area of this shaded region times this value YC. What's the area of the shaded region? You know, it's a rectangular shape, so that's going to be 0.25 times 0.1, so 0.025 meters squared. And what's YC? So it's 0.25 plus another 0.125, so YC is 0.375, right? And so Q is equal to 0.025 times 0.375. Can someone multiply that out? Let's do it by hand today. Next time. 0.00937. What? 9375. Okay. So the absolute value of this shear stress is equal to 490.5 times 0.009375 divided by I is 0.001041 times B is 0.1. And what do you get for that? Okay, so 4, what's that? 444 times 10 to the 4 pascals. That's the absolute value. So now we have to think about the sign. What direction is the shear force at this point? So at our cut, okay, so this is the edge that we're looking at. We have a shear force that's negative, right? So what direction is that shear force? Yeah, exactly. So V is up, and that means that the stress element looks like this. These values are all 4.4 times 10 to the 4th. And so is tau xy positive or negative? And how do you know? Yeah, because it's on the x face in the positive y direction. So tau xy is equal to positive 4.4 times 10 to the 4th. Yep.
How is YC 0.375 if it's 0.5 control?
Yes. 0.18. Yep. I screwed that up again. So this whole thing is 0.25. So this is I messed these all up. So the area is 0.125. Yep. Okay. So this is 0.0125 meters squared. YC is, what's that? 0.18, what did 18 what? 75? 1875. So this is 0.0125 times 0.1875. So can you multiply that one again? 0.00234. For Q? That's Q?
Yeah.
Okay.
And tau is just part of that, so 1.1. So I'll just divide it by 4.
Okay. So 0.0234. So 1.1. Okay, thanks. The directions are all still the same. So 1.1. This is 1.1. Okay, so the final answer is the stress tensor is equal to we had 5.9 times 10 to the fourth in the XX position. Then we had 1.1 times 10 to the fourth in the XY position, zeros. What else? Is anything else non-zero? Yeah, YX has to be the same. It's symmetrical. So we have to have this, and then everything else is zeros. And if we calculated the strain, like if we knew what type of material it was, what elements would be non-zero for the strain? So the only thing that's affected by the XY stress is the XY strain, so that would be non-zero. And then there would be an XX strain, but then there'd also be a YY and a ZZ strain because of the Poisson's effect. Okay, so because this thing is elongating, well, let me draw it in the right direction. So if you think of this as being the starting point, that's X, that's Y. It's going to get longer this way. Obviously, I'm exaggerating this. So it's going to stretch out in the X direction, and it's going to contract in the Y and Z direction. The Z direction is into the page. Okay, that's the Poisson's effect. Any questions about that? Remember talking about that stuff. And then what's going to happen with the shear? We're going to have a positive XY strain. So what's going to happen to the angle between the positive X and positive Y faces? Is it going to get more acute or more obtuse? It's going to get more acute, yep. So this is exaggerated, but you'll end up with a strain that looks like this, and you'll have non-zero values here, 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 and here for the Voigt strain. Any questions about that problem? Okay. If I had asked you for the stress at the top or the bottom, there would have been a stress due to bending, but none due to shear. If I would have asked you at the middle, there would have been a stress due to shear, but none due to bending. Okay. All right, so there's only one other type of cross-section that we're able to calculate stresses due to shear force for, and that is for a circular cross-section. So we're looking for the maximum XY shear stress in a circular cross-section. and that occurs at the neutral axis. Okay, so if our beam is like this with a circular cross section, and X is this way, Y is this way, and Z is out towards us, and we have some shear force V, the maximum shear stress is going to be along the neutral axis. We can't calculate tau xy anywhere else on a circular cross section. Okay, so what does that mean about the importance of bending moments when we're doing calculations involving circular cross sections? What? It's at the center. So there's no, so if I ever ask you to calculate a stress with a circular cross section, you don't have to worry about calculating it for the bending moment because it's at the neutral axis. There's no stress due to the bending moment there, right?
Does that mean only share only at the same time?
Well, no, it doesn't. It just means we can't calculate it. It gets more complicated other places. So this is all we can calculate. And so what that means is that simplifies calculating Q. Because it's only at one place. So we can just come up with a formula for Q for a circle. Okay, so if this is your cross section, this is the neutral axis, and we're going to calculate the shear stress at the neutral axis, then what's the area that we're going to use to calculate Q? This? That little star? No. Yeah, the top or the bottom. So that area, and then the centroid is this. Okay, so this is y sub c. Y sub c is, you can just look this up in the centroid formulas, and this is 4r over 3 pi. And so Q is equal to the area, which is pi r squared over 2, times y sub c, which is 4r over 3 pi. You get some cancellations and stuff, and you end up with 2r squared over 3. Okay, so r 2r, that must be r cubed. I must have just written that wrong. Thank you. And it has to be because the units have to be meters cubed. So that's the only Q formula you need for a circular cross section. Okay, and then everything else is the same as for the rectangle. You just can't do anything besides the center. So here's an example for you to work on. So let's say that you have a cantilevered beam. And let's say that there's a tension of 20,000 newtons. And the mass is 1,000 kilograms. And the cross section is circular with a radius of 0.2 meters. Let's say that this whole length is 1 meter. Calculate the stress tensor for a point on x equals 0.5, that's that dotted line, at the neutral axis.